Okay.
But now that I've pressed the button, we can't do any kind of like fake joking about some sort of topic, which is a staple of the podcast. But now the joke is that I've said that, and actually it's all real.
Wow.
All right. So, just gonna let it actually. It goes the
Just
other
let it
direction.
just let it sit for a minute.
My reflex is to give it time to start streaming before I say anything, but on YouTube especially, it goes the other direction where it's stuff
Mm-hmm.
before then. So, anyways. Hello there, everyone, and welcome to Tapcaf Transmissions, the only Star Wars podcast that is currently airing on this channel. We've had to be a little bit more specific. The lawyers have got to us. There are apparently other Star Wars podcasts. I
No, that's not
am
what they said. They said there could be in the future, and they wanted to cover us just in case.
okay. Well, you are the professional lawyer here. Isn't that true, Mr. EckhartsLadder? That you are a professional lawyer still?
I mean, I can't technically practice right now because I've suspended my license because it's like 10. Well, not 10,000. It's like $8,000, I think, to
That's
have an
wow,
active license, and
per year.
it's still like yeah per year.
That's
It's
like
still
three
like
sponsored videos.
3K.
That's ridiculous.
I mean, it's still a lot of money. But additionally, the more troublesome part is I've got to do a bunch of professional hours if I'm not suspended.
Hmm. Well, joining us today is someone who is actually practicing in their field. See how I segued that? That was the perfect setup. A good friend of mine from the Empire at War modding community who's here to talk to us about science, actual science in a fictional science fiction scenario. We have Dr. Andrew Fullard here to talk about astrophysics. How are you doing, Andrew? I don't know if I'm going to be able to do this.
It's okay, you can. If you slip into Bob all the time, that's fine. But hello, everybody.
Hey, wait a minute.
You can
Your
call me
name's not
Doctor.
Robert. I'm just putting it out there. Just shaming him live in a private conversation we had beforehand.
All right, so today's podcast, we have put out a call for questions over the last couple of weeks to get some topics that you guys want to hear about, talking about the, let's call it the relationship between Star Wars and science, especially astrophysics, because obviously Star Wars didn't happen, so a lot of the stuff is made up, but wouldn't it be cool to see how stuff could work if it did work or if it did happen? And that's kind of what we're going to be talking about today. So, do you want to kind of give some background on what you do or how you got into Star Wars, Bob? Andrew?
Sure. Yeah. So I'm currently working to simulate the light from supernovae. So supernovae occur when stars explode. So that's always pretty exciting. I've been looking at both types of supernovae currently in my work, Type 1, Type 2.
Which
So
one's
that's
cooler?
when
Which is the one that you're
um,
born with, and which one do you get?
Sorry, continue.
which one's cooler is a great question. The cooler supernova is probably, I want to say, Type 2, because that's the one that can create black holes a bit more easily.
Mm-hmm.
But basically the difference between them is whether they have hydrogen in their spectrum or not. And there are some Type 1s that are from massive stars. It's a whole thing. The classification systems in astronomy are ridiculous, but yeah, that's what I study, stars that explode. So
So I was gonna ask, what's your day look like? Like what's a day in the life of an astrophysicist
so
studying?
I wake up, I get on the computer, I do science, then I leave the computer and I go to sleep. But more seriously, most of my day at the moment is dealing with managing a research team.
Mm-hmm.
So that's, if any of you are undergraduates currently, I'm one of the people who tells you what to do. Uh, so I apologize for that.
Mm-hmm.
And yeah, astronomy these days. It's not people going out to stick their eye to a telescope. It's very much sitting at a desk, working at a computer, and ideally getting data from telescopes.
Waiting
But
for the
usually that
email to
data
come
will
in about when you're going to get your data from the telescope?
precisely, yes. And then the other rest of the time is spent begging for money from the government.
Right. I mean, so basically what you're saying is you're just playing Universe Simulator all day and discovering the hidden truths of the universe.
Yes, I know I really sold it to everybody there, but it is really actually a very fun job.
No, it sounds awesome.
So what would be the smallest projectile necessary to cause a star to go supernova? Could a sun crusher
Small.
exist?
You really
you
wanted
ever
to lead with that one.
Have you ever seen
Wow.
any of the supernovae that you've studied? Have there been any that you suspect were made by an angry emo kid who just left Jedi school?
I'm afraid I have to say no, but there are some very strange supernovae that we don't really understand properly. They have weird signatures in their spectrum of elements that shouldn't be there, or they have strange information that just doesn't really make much sense. And there are a number of classes of supernovae we still don't understand how they're produced at all, or how they're connected to other events. So one of the big things that I worked on as part of my graduate school work was trying to understand which kind of stars produce gamma ray bursts, which are events that produce very focused, high energy light in the form of gamma rays. That, by the way, if they went off really close to Earth, they would probably sterilize the planet. They're pretty crazy
Honestly, we could
things.
use that at this point. Let Mother
But
Nature have her back.
What's the closest one that would have been able to do that if it were closer?
I think probably the Crab Nebula was. I don't think there was there may not have been a gamma ray burst associated with the Crab Nebula, but the Crab Nebula exploded. I believe that one was in 1054 AD. That Crab Nebula was created. So that was actually observed by historical astronomers in China in particular. We have a lot of records that they took, so we can actually construct what's called a light curve of the supernova, where you can track how bright it is over time, and that tells us a lot about what kind of event it is. Currently, in the center of the Crab Nebula is a pulsar, which is a neutron star, which is very rapidly spinning and kicking out radio waves. So it's a very interesting object.
And those gamma ray bursts are traveling at the speed of light, right? So we won't even see it coming. We'll just be gone.
Well, it depends how far away it is, really, because as you may know, a light year is a measurement of distance, not speed.
Mm-hmm.
Same as a parsec, which obviously Han Solo wasn't aware of at the time.
Well,
Yeah,
we get all those fun retcons on how it turns into like the route through the Kessel Run. So that was corrected in post, at least.
I hated that. I liked Han just bullshitting better.
Yeah, that Han never studied. Get that hashtag trending, everyone.
Yes, we do have a lot of questions. You guys emailed us a lot of really interesting ones, and we're going to go for a bit, and then at the end of the episode, we're streaming this live, of course, for anyone listening. We will also take some chat questions if there's time. So if you hear something that you're interested in as we're talking about it and you want to learn more, feel free to keep your question ready for the end of the episode. If not, send us an email and maybe we can get some answered in the future. But Corey, do you want to lead off with the first discussion point here?
Yeah, actually, before we get to the questions that were sent in, I do want to kind of ask more personally, like, how did you, if you want to talk a little bit about maybe how you got into Star Wars and how you got interested in science and kind of how you kind of went down that path, and if that ever intersected for you, or if it was just coincidental that you were interested in spaceships separately from studying stars.
I mean, I've always been interested in space ever since I was a young child. Like, there's the classic, the cliche looking up at the night sky and stuff, but I lived in a relatively rural area as a kid, so there was a decent amount of that. And my mum in particular was a big fan of Star Wars, so I ended up seeing the originals. Basically, I ended up I remember seeing The Phantom Menace when it came out. And then after that, because I guess I'd really enjoyed it at the time. I don't have a huge amount of memory of it, but I really enjoyed it at the time. My parents got me the original trilogy on VHS because, of course, they'd just come out in the specialized Lucas edit.
Hmm.
And yeah, and I just really loved it. I really enjoyed, like, the epic adventures, and it really did, like, help reinforce for me the idea that space and science was a cool way of exploring the world and the universe. Um, yeah, so it was really, they did kind of intertwine at multiple points. I mean, I continued, um, like, in I will say that, in particular, Star Wars gaming um, was a pretty big deal for me as well. I remember playing the original Star Wars Battlefront on PlayStation 2. Um, Played that a great deal. And then, weirdly enough, when Empire at War came out, one of the first things I did with that was try and mod it a bit. And that really actually helped spur my interest in working with computers and has led me down the somewhat more theoretical path of astronomy that I'm working on these days. So I'd say, yeah, they've definitely both informed each other and pushed me along in different ways.
Do you ever feel like, I don't know, a little disappointed by like all the physical realities of the universe? Like we'll never be jumping through hyperspace to across the galaxy or anything like that, and we'll never have, ships that can fly like the X-wing. I don't know. For me as a kid, like I would guess say I was disappointed when I saw the first, like when I really started paying attention to the first, because I grew up from Star Wars from the point like I can remember. So when I was old enough to be interested in spaceships, I was like, oh, these aren't really what I expected them to look like.
Yeah, I mean, I think I was always aware that Star Wars was definitely more space fantasy,
Mhm.
than true what a lot of people consider science fiction. Like, even if it's science fiction, it's on the soft end.
Mhm.
Yeah, for sure.
And I think that meant that I was always quite happy to, like, disconnect the expectations there.
Mhm.
Certainly, like, there are certain points in I feel in a scientist's career where you will have that feeling where you think, oh, maybe this isn't as interesting as I thought it was. But then something new will come along and you'll say, oh, but actually, this really is quite cool because we don't actually understand this properly.
Mhm.
And I'm always reminded of in the late 19th century when Lord Kelvin said, oh, that's it, physics is done. And then 20 years later, Einstein and relativity and then quantum mechanics came along and
Mhm.
completely almost like overnight changed the way we think about the universe and how we understand just basic things like matter and energy.
Well, you're an interesting
So,
time because you're kind of in the point where they're putting everything together. They're trying to, unify the two major like remaining arms of physics. So is that something that like you study, or like that you're interested in still, or that it's cool to be a part of, or do you like to stay in your little niche, I guess?
I mean, I'm pretty happy in my niche. I think things like the idea of a grand unifying theory is one that I feel is very it's optimistic still.
Hmm.
Definitely there are plenty of brilliant theoreticians who are making strides towards that kind of thing, but there are so many other questions that we still don't understand how to answer.
Hmm.
Um, like basic stuff, like, as I said, which, when we see a star explode, how did it explode? Why did it explode?
Hmm.
When, like, um, we've only recently been able to properly capture neutrinos from the sun, which is something that was predicted like 70 years ago to explain how the sun could glow. So there's still loads of things that people can predict and people need to investigate to really understand what's out there. And I think it's always nice to feel like you're contributing something to the kind of sum total of human knowledge.
Yeah.
That's like one of those like overarching things where I feel
Hmm.
like, yes, maybe 10 people will read my published paper, but it's out there, people can read it. It's providing something to the community. And especially what I'm working on now, where I'm working on the simulation stuff, we're making it open source. Um, and the idea with that is that, yeah, the whole astronomical community can use this tool and really push the envelope in their own work. And so
Hmm.
being able to contribute to things like that is really exciting.
Hmm.
Yeah.
Well, you touched a bit on relativity there. I know that was something that Eck wanted to bring up because what I wasn't relatively recently, but it's been established at least that relativity does not exist in Star Wars when it doesn't need to.
Mhm.
So, it could you even
Talk
fathom like what a universe without relativity could look like?
and give a brief rundown of what it means for those who don't know.
Yeah, of course. Yeah, relativity is it's not quite as difficult to grasp as quantum mechanics, I would say, but it's still an incredibly it's a theory that has extremely deep ramifications for how we think about the universe and how we think about basic things like the forces that act on us every day. So the first thing I'd like to say that all the observations we continue to make continue to affirm the extreme precision of the theory of both the special and general theories of relativity. We get one of the classic observations is actually pulsars again. You can look at if two pulsars are orbiting each other, you can and so I'll roll back a bit. So pulsars are rapidly rotating neutron stars. So they're made of one type of elementary particle. They spin very rapidly. They put out radio waves at their poles because of their magnetic field. So we can detect these radio waves, and because they spin, if they are off axis to our line of sight, they essentially flash in a very
Mhm.
regular way. The woman who discovered these, Jocelyn Bell Burnell, initially thought they could be aliens. Um, and unfortunately, she's probably one of the biggest Nobel Prize snubs. They gave the Nobel Prize to her advisor instead of her because she was just a student at the time and a
Ugh.
woman.
Yeah.
She's still alive. She still does incredible science. But But these pulsars, what happens when they orbit each other is you can time the orbit incredibly precisely. And you
Mhm.
can see that when you do that timing, it follows the theory of general relativity perfectly down to extreme precision, 1 in a million precision or more.
Doesn't it
And
help? Oh, sorry.
no, carry on.
I was gonna say, doesn't it help? Like, doesn't relativity help explain some of like the nuances of orbits in our solar system that like general mechanics
Yes.
can't?
Yes, exactly. So there are two kind of main theories of general relativity of relativity that I mentioned. There's special and general. Special relativity is mainly concerned with what happens when the speed of light is a constant, which as far as we know it is.
Mhm.
And that has impacts on things like time dilation. Um, you get more massive when you go faster, weird effects like that. And then the general theory of relativity expands that framework to describe the whole universe, and as a result gives us the concept of what's called space-time, which is essentially the idea that we are living in a four-dimensional space, which is 3 dimensions of space and 1 dimension of time, and they are all one thing, so that if you move in time, you can move in time and space simultaneously but also separately.
Mhm.
So if you remove those theories, yes, as you say, one of the things that relativity does explain is a thing called the precession of Mercury. The planet Mercury orbits the sun in such a way that it defies explanation through standard Newtonian physics, which is probably what you learned in high school. That's GMM over r squared, for the law of gravity. In general relativity, you explain orbits through mass warping space-time. So the classic visualization is you put a bowling ball on a rubber sheet,
Mhm.
Hmm.
and then you send marbles around it, and the marbles follow the path. And the same happens to everything that follows the curve of space-time around a massive object, light as well. One of the major early experiments that verified general relativity was the eclipse experiments done by solar eclipse experiments done by Eddington, where in the early 1920s or maybe early 1930s, I forget, it was probably 20s. Um, they checked the positions of stars before and after like during an eclipse, and they found that when the stars passed near the sun during the
Mhm.
eclipse, their position was incorrect, but it was incorrect by the amount that general relativity predicted.
Right.
So if you remove all of that from the equation, you start to get very weird things happening. Like if you remove special relativity, the speed of light is no longer a constant. So light can speed up and slow down. Well, you can already slow down light, but light could go potentially faster. You could send photons at higher than c. And you get really weird stuff like you won't be able to explain certain phenomena. Like there are these jets um, that come from galaxies,
Hmm.
where the black hole in the center of the galaxy is kicking out material at a high speed, like about 95% of the speed of light. But
Hmm.
because of relativity, the angle at which the light comes to us means that as a particle moves along the jet, it appears as though it's moving more like 6 or 7 times the speed of light.
Hmm.
It's a really interesting phenomenon, and if you look it up, I believe it's called no, it's not relativistic blue shift. There's another term for it, but I can provide a link to the paper about this stuff for later. But um, that kind of thing wouldn't happen, and in fact, probably what would happen there is these jets from galaxies would go faster than the speed of light, and they would essentially accelerate almost infinitely. Um, what happens is currently, if you accelerate something as it reaches the speed of light, it will slowly become more and more massive until it effectively slows down.
Hmm.
It slows its acceleration and approaches the speed of light. But if you can go past that, you can just keep accelerating forever. So that means interstellar travel would be much easier because you could
Hmm.
just accelerate something and eventually it would be going fast enough that it could get anywhere within a reasonable amount of time.
Right. So relativity like is often used as sort of a in science fiction. Like you see an interstellar special relativity that play with it a bit, like when they're at the black hole and the shifting time depending on how close they are to the mass. But in a lot of softer science fiction like Star Wars, right? They just ignore it and they let like Star Wars has faster than light travel, it has faster than light communication. It's just not even really a consideration. Um,
Exactly. Though it's interesting that still certain predictions of relativity are included in Star Wars, like black holes. Corey mentioned this, and I had a quick chat with Corey about this before we started the
mm,
episode. But black holes existing in Star Wars implies there is some form of space-time singularity, because that's what a black hole is. It's essentially a situation where you have infinite density,
mhm.
and that creates such a deep well in space-time that not even light can escape. In Star Wars, for that to be the case, because light can go almost arbitrarily fast in a world without relativity, then these black holes in Star Wars must be even, well, the thing is, for a black hole to exist in Star Wars, there must be some form of space-time warping, because you cannot make a massless particle like a photon, which is what light is made of. You cannot cause a massless particle to be affected by gravity because it has no mass. The only reason that light is affected by heavy masses is because they bend space-time. So for a black
Right.
hole to exist in Star Wars implies there has to be some form of space-time. So, but maybe it's just that space gets bent by black holes in Star Wars, and time isn't actually affected.
It does kind of
That's
seem
one
like that's
possibility.
more how it leans because I know something that we've spoken about before as well is that in a lot of situations, uh, black holes in Star Wars just work by vacuuming up stuff and not really having
Mhm.
an impact on anything around it either. The Dovin basils of the Yuzon Vong, where they kind of just act as shielding, absorb things, and then disappear,
Mhm.
kind of work more in that way.
And you can blow them up.
Yeah. So you're
Yeah, I
saying
suppose
that Dovin basils aren't possible, apparently?
I would say that they would be, technologically speaking, a challenge, as a bit of an understatement. But the idea of small black holes that you create and then become destroyed is not completely unreasonable. One of the big hullabaloos
Sorry. I
about
remember.
CERN.
Yeah.
Yeah, I remember this.
So about CERN, when they put the Large Hadron Collider online, people were terrified they would create a black hole and it would suck the whole Earth in. But even if they created a black hole, there is a process called Hawking radiation discovered by Stephen Hawking, or postulated by Stephen Hawking. I don't know if it's been empirically observed yet, But Stephen Hawking has postulated that black holes radiate very, very slowly. They radiate long wavelength light in the form of essentially infrared radiation, so like heat radiation essentially. And that very small amount of radiation essentially causes the black hole eventually to evaporate because they're losing energy, and energy equals mass under relativity. So as they lose energy, they lose mass, and eventually they effectively evaporate. And very small black holes made with very little mass will therefore evaporate very quickly under Hawking radiation. So even if CERN did create a tiny black hole by smashing protons together, which is very unlikely, it would evaporate almost instantly and leave nothing behind except a few photons.
So how
so
does...
Dovin Basel could create a small black hole in that sense.
Interesting. It's crazy that, like, I know Stephen Hawking and others did a lot of work around black holes, but it's crazy that Einstein kind of just, what was it, like early, like 1908 or something, kind of just, nailed this shit out, and just it ended up mostly being correct.
Yeah, the creation of these theories of general and special relativity is certainly something that I recommend anyone read books about Einstein's life and how he came up with this stuff. It's very impressive. Also, not to forget the roles that his partners played in this. They often did the mathematics because he had some trouble with mathematics occasionally. Not as much trouble as people like to say he had, but still, he did have. He was not working entirely alone on these things, and other people had come up with ideas to describe space-time. So, for example, there's a thing called the Minkowski metric, which is one of the standard ways you describe space-time as a set of small pieces. If you've done calculus, they're infinitesimal pieces, but you can describe space-time with these metrics. And this metric, the Minkowski metric, was actually something that was created before Einstein used it to help describe space-time. It was actually created by one of his professors. So yes, the man was definitely a genius, but it's always important to remember that none of this science comes from a vacuum.
Right.
Especially, that's even more true nowadays. I work in a team of about 30 people working on the stuff I do. And you look at the collaborations like Large Hadron Collider, if you ever see any of the scientific papers, generally the first 2 pages are just filled with people's names. With the hundreds and hundreds of people who've worked on these experiments, building them, testing them, designing them, running them, interpreting the results, and writing the papers.
It's just it's crazy to me as somebody who's not scientific at all. Like, I only understand some pop culture science. Like, how much of... We should get him on the podcast, Einstein. I think I've got him on Discord.
Oh, Justin, I have some bad news about that. I'll tell you after the show.
Okay, thank you. Like, I was reading about how there were even parts of his, like, equations that he thought were mistakes that would end up kind of reveal.
Yes, I can talk about that. I can talk about that a little bit if you like.
Yeah, please do.
So over the last probably 20 years, there's been something of a revolution in cosmology. Cosmology has a lot of revolutions because cosmology is very poorly understood. But the general idea is that basically before we started looking at more detail at distant galaxies, we didn't really quite know how fast the universe was expanding. We had a good idea from stuff that Hubble had started in the late 1920s, but since we've had more powerful telescopes and more deeper surveys, we found actually that the universe is not expanding uniformly; it's expanding in an accelerating manner. So it's actually expanding faster and faster. That means that there has to be a force putting pressure on the universe to make it expand faster. Space-time has to be being pushed by something for it to expand faster. And because if it was just the Big Bang that initially causes an expansion, and then that expansion just continues because nothing stops space-time except more space-time. But if that was the case, you would expect essentially a constant acceleration, or sorry, not a constant acceleration, a constant expansion rate modified by the shape of space. If space is flat, it's constant. If space is closed, which means you can think of it as a sphere, a closed space-time means if you drive around it, you'll come back to where you started. It's very weird.
It's like a
very, very
balloon,
weird.
right?
Yeah, yeah. In that case, eventually, the space time will start to collapse on itself, or an open space time, which is what we seem to be in, which is shaped more like a saddle, where
Mhm.
everything just continues to accelerate further and further apart. And this actually, Einstein originally put in something called the cosmological constant because he liked the idea of a steady state universe. His equations initially predicted that the universe should expand, and then he put the constant in to stop it expanding.
Mhm.
Then Edwin Hubble discovered that it was in fact expanding by looking at galaxies in the distance, like distant galaxies moving away from us. And then Einstein said, "Wow, I was an idiot. Let's get rid of that cosmological constant." And then now we've looked at galaxies, finding they're accelerating away from us. And that means we need a cosmological constant, but it's kind of the opposite of what Einstein originally proposed, and one that's creating energy out of nothing, so-called dark energy.
Right. And we can actually bring that back to Star Wars a little bit because I know in canon they say the First Order. I remember this because it's such a weird little bit of lore. In the novelization, the Starkiller base uses quintessence, which I think is somehow related to dark energy. Do you know anything about that?
I haven't read much about that in particular, but that sounds like one of the classic ideas of what's called exotic matter.
Mm-hmm.
And dark energy, like, we understand so little about it aside from the fact that it needs to exist for our theories to make sense. It being a kind of exotic matter isn't unreasonable, and I can talk a bit more about exotic matter in a little while when we get into some stuff about hyperspace. But basically, the idea of things like exotic matter is usually they'll have something like negative energy
Mm-hmm.
or some other really weird properties. They'll be incredibly massive particles, that kind of thing. So yeah, that kind of thing is interesting. It's interesting that seeps into pop culture over time, and
Mm-hmm.
it doesn't help when astronomers pick names like, or cosmologists pick names for things like dark energy. Um,
Or like on the
though,
other end, like quarks or
oh
like
Yeah.
the subatomic stuff. They always have the
yes,
funniest
yes.
names. That's
So
just like,
quarks are actually named after a line in a poem, I believe, that a particle physicist thought was quite nice,
yeah, I think I
and they
heard that on
just
the
went for
radio.
it.
So do you think that harnessing dark energy, I like there that's a pretty common thing in science fiction. Is that a good way to power your weapon, do you think? Because is it some hidden source of energy throughout the galaxy waiting to be tapped into, or what?
It's not completely unreasonable, but the thing with dark energy is even though it makes up something like 75% of the mass energy kind of content of the universe, according to our calculations, it's spread out throughout the universe. So it's incredibly low density. And that's another thing if we want to talk about Star Wars asteroid fields and the like the reality is space is very empty
Mm-hmm.
and incredibly low density. And even things where you're like, wow, that's a really dense part of space are incredibly localized and very small in comparison to the rest of space. Space, to quote Douglas Adams, space is unimaginably big.
Mm-hmm.
And being able to kind of collect enough of that energy to do something with it would be very difficult. And you probably would need a planet-sized thing to do so. So,
I feel like the movie maybe takes away from that when it shows it's just sucking up a star. I don't know.
The solar
yeah, because
vacuum.
that's just fusion power at that point.
I think they got
Yeah.
that from watching Spaceballs, because I think the vacuum does that as well.
Yeah, it does.
But but I guess if we do want to get into the first of the email questions, because a lot of this does kind of tie into
Mhm.
talking about hyperspace and asteroid fields, which are probably some of the bigger topics we were asked to talk about. But our first email here asked a few questions. There were a few requests to kind of come up with pseudoscientific explanations for how maybe real world versions of certain Star Wars tech could work or could look, breaking as few laws of physics as possible. So the two main requests there, I think, were shields and hyperspace. So if there's either of those that you really want to touch on, like maybe ideas for how we
So
could get hyperspace with breaking as little as possible.
I'll start with hyperspace because that's most directly relevant to what I was talking about. But one of the things I would suggest people look into is a thing called the Alcubierre drive. That's Alcubierre. The Alcubierre drive is the idea that to go faster than light, you don't have to go faster than light. You make space-time around you go faster than light. The restrictions in relativity say that matter can't go faster than light. They don't say that space-time can't go faster than light. So what you do is you use exotic matter with some kind of negative energy or some other ridiculous property. You bend space-time such that it compresses in front of you and extends behind you and pushes you forward while being stuck on this little bit of unmoving space-time. And as long as you are not moving at the speed of light or near the speed of light, you can just happily skip along through the universe along that bit of space-time, just warping and ultimately this comes down to a lot more like the classic Star Trek warp drive. That's the kind of thing that they were basing the warp drive off in Star Trek. Hyperspace in Star Wars is probably more like a wormhole. I know that someone asked the question saying, could hyperspace be traveling through a different dimension or be like traveling through a wormhole? The idea of different dimensions or dimensions beyond the four that we know of, which is X, Y, Z, and time, is difficult to consider. String theory, which again was mentioned in this kind of set of questions, postulates that there are up to 11 dimensions. However, all the dimensions above the ones we see are actually kind of contorted and crushed down onto themselves so that at every point in space-time, in our space-time, at every point, for whatever value a point has, which again, I can talk about quantum mechanics a bit later as well. But at each point in space-time, all of these other dimensions are kind of like wrapped down and crushed down into these ridiculously contorted, highly complex geometric shapes that can be described with mathematics but can't really be visualized.
Right.
The thing to look at, there's a thing called a Calabi-Yau shape or a Calabi-Yau diagram, which shows kind of what these things should look like if they were presented in 3D. And people see drawings of hypercubes, things like that.
Hypercube, that sounds cool.
Not a great movie.
Four-dimensional cube.
I heard, because I was listening, we have got a astrophysicist on my local talk radio station who comes on every couple of weeks to talk about stuff like this, and he mentioned how kind of modern views of string theory, they have like the strings kind of folding into themselves, so not particularly useful for any kind of long distance wormhole interdimensional travel.
Exactly. They're more like, instead of strings, they're more like little donuts.
Right.
And they vibrate and oscillate and create all the science and particles that we know of, but you can't really do much with them. The other option that's a bit more like hyperspace is a wormhole. Wormholes are something that's postulated and possible within general relativity. Instead of using other dimensions, essentially what you do with a wormhole is you bridge space-time in a more direct manner. You make a giant hole at one end with some horrible exotic matter. You make a giant hole at the other end with some exotic matter, and that bridges the gap. And it's a lot like, there's a really nice diagram actually on the Wikipedia page for wormholes. It's a decent page. You curve that, or essentially, if you imagine a piece of paper, you fold it around so that one end is kind of like a curve, and then you punch a hole through it. And then you can look through that hole, and if you imagine someone on one side of the piece of paper, they can go through that hole and get to the other side almost instantly, compared to going all the way around the edge of the paper or all the way over the surface. And that's kind of what a wormhole would do. And I think that's probably the closest to what we see in Star Wars, where hyperspace looks like a tunnel.
Right.
And you have like warping and complex lighting effects around it. That's the kind of thing you would maybe expect from a wormhole.
So in that kind of framework, the most realistic version of hyperspace we actually get in Star Wars would be more like is it the Falinasi who have the kind of insta drives, Heck? Or is it's the Ang-T?
No,
it's the
Ang-T, yeah.
Yeah, and I think that's because wormholes could be arbitrarily short, probably.
Right.
If they were possible to make, you could essentially just like step into a wormhole and step out the other side and be in the other place.
Right.
Do you ever just feel like physicists are just making stuff up, like to see how far they can take it? Like, oh yeah, strings and negative energy and quarks.
Honestly, I mean, you're not that far off. A lot of these kinds of theories arise because
trying to fill
physicists
in
look at the
holes that we don't
mathematics.
understand.
Or they look at the mathematics and say, what happens if I take this to the extreme?
Mhm.
What happens if I change the numbers? Like, what if I put a negative energy into Einstein's equations? What happens then? And then you try and understand what the equations are telling you. And that's like the core of theoretical physics, is really looking at the mathematics and trying to understand what happens when you push your mathematics to the extreme.
Mhm. I don't know. I kind of feel that way about dinosaurs too. Like they're kind of just fucking with us to see how long.
Well,
I
that's
mentioned
for
this
our
recently,
biologist episode.
okay. You just want to
Yes,
talk about interspecies mating,
No,
Corey.
you just want to talk about that, but I feel like we're gonna get Andrew fired if we go too far down
Guys.
this. But yeah. So
I can go on to shields now because I
oh,
did
do you
a little bit
have?
of research
I didn't
on
want to
shielding.
force you to talk about shields because I feel like that might be a little bit more outside of your specific area. But if you
Shields aren't too bad, at least the idea of ray shielding, because specifically from what we can tell looking at Star Wars weaponry, it seems to be plasma based. You have hot gas, Tibanna, of course, that's blasted out and it glows, which means it has to be extremely hot so that you've got like free electrons in the gas that then recombine with the atoms, and that releases photons. And that's another thing that Einstein helped us understand. And so, if we're seeing light coming from these things, they have to be really hot, and they're probably ionized, and so they're probably a plasma. And the easy way to stop a plasma in its tracks is use magnetic fields, because if you have a charged particle, it experiences the Lorentz force in a magnetic field, which causes it to follow the magnetic field. And that kind of thing is why we have the aurorae on Earth, because the magnetic field of the Earth effectively acts like a Star Wars ray shield. We have charged particles that come from the sun and interact with the magnetic field of the Earth, and they're channeled into the magnetic poles. And as part of that channeling, you get the aurorae because these particles are basically dumped at the poles, and then they just bounce around in the atmosphere and cause a bunch of chain reactions,
So
essentially, that create photons and light.
so would that require then some sort of substance or matter to interact with? Like, would you be able to do that around a ship without kind of expelling some matter to do that with, the way that happens in the atmosphere, or would you then be able to have like shielding in an atmosphere, but it'd be more difficult to do it in space?
I think it would be fine to do it in space or in atmosphere as long as you weren't in a place that was heavily charged. Because what I would imagine is you'd have these localized magnetic field generators that create a magnetic field that is pointed in such a way that the generator itself absorbs the energy from whatever weapon you
Right.
hit it with. So if you hit it with the Turbolaser, it absorbs that Turbolaser energy, and that's why shields have, in games, that's a good way to explain why shields have to be recharged or why they can be overwhelmed, because eventually you can imagine them as like mini aurora in the shield generator. Eventually will overwhelm the generator's capacity to absorb that energy. And so then it probably has to be like vented out of the ship, or it will just cause damage to the ship. And that's the way you can do ray shielding. Now, particle shielding is a lot more difficult because most particles aren't charged. Where I talk about particles here, I mean like things like dust sized or bigger, because technically all of plasmas are particles as well. They just happen to be particles that have charge to them. So if you have uncharged items like a warhead or an asteroid or something, to stop that, the only real way to stop an uncharged object is through the use of gravity. That's like the easiest thing to do. So you would have to have some kind of local gravity field. And clearly Star Wars ships are capable of producing those, otherwise they wouldn't have gravity on board.
Right.
So it's not completely unreasonable for their particle shields to essentially be localized gravity projections around the ship that warp space-time and mean that any projectiles that hit them are essentially deflected off. Now, that doesn't... Sorry,
carry on. No, go ahead.
I was going to say that, of course, doesn't really quite mesh with what we see, where, if Star Wars ships get hit with rocks, they don't tend to just bounce off the shield necessarily, but they tend to explode. But again, that's what with what I know of physics at least, and what we know of physics as far as I know is that gravity is the best way to deflect that kind of thing.
So we
So could
actually do come back to the Dovin basals. Go ahead, Ek.
Oh, I was just gonna ask if like, is there any way you could? Because I always figured that the shields were like just making some sort of energy that was destroying the projectile. Is that something that would be possible? Like, could you
Yeah,
make?
that's the other way. It would essentially be like you would have to be always putting out energy at some frequency that
Right.
presumably isn't visible. Like you could be emitting gamma rays from your ship all the time.
Hmm.
And you could do that, and essentially that would be like exerting a pressure, because enough photons can exert pressure on um, matter, which is why Count Dooku's solar sail ship works. Um, at least for short trips. I wouldn't want to use that for interstellar distances. It
Hmm.
would accelerate up to near the speed of light, but then it would just kind of sit there. But I guess, I don't know, without relativity, perhaps the solar sails work really well.
I'm just
And you can
picturing
just
Dooku
shoot up.
surfing now with that.
But yeah, that kind of thing, that is another way to potentially think about that. Like I was thinking about how you would set up some kind of energy-based barrier like that, and it's a difficult question, definitely. And I'm sure there are people who have thought of better ways of doing it than I can think of
Well,
in a
it's
week of doing research.
no. There's actually going to be a practical exam after the end of the podcast where we get you to build at least one of these technologies. But it's interesting that you bring up the solar sail thing because one of the things we see, especially in some of the Bantam era Star Wars, is like the etheric rudders that fighters
Mm.
have, where it's the idea that instead of being mostly a void, space is full of this other substance, and
So the ether is an interesting idea because
an older idea, but it checks out.
well yeah, so that was again, that's one of those classic, that's one of the idea of the ether is one of the reasons that Einstein came up with the special theory of relativity, because it was never clear, because the way that we had theories of light in the 19th century is people had thought it was a wave because it behaved every way they could test it with the equipment at the time. It behaved like a wave. You could split it with a prism, you could diffract it, you could do loads of cool stuff with lenses. That's what they could do with it. And then a bit later, and as sorry, and as a wave needs a medium to travel in.
Mhm.
You know, like a wave on the water doesn't mean anything if the water isn't there.
Right.
Mm. Like
Sound
sound
wave
doesn't
doesn't mean
travel. Yeah.
anything if this. Yeah, exactly. So they proposed a thing called the ether, which was going to be a static field that permeated the universe that light would travel in. You know, about it's along the same lines as dark energy. Really, it was scientists trying to explain phenomena based on the theories they knew.
Hmm.
And so people tested you could test for the existence of the ether, because if the ether was a stationary field, as the Earth moves through space, you should see the effect of the ether on light, because it would compress the light waves as you move towards the ether and rarefact them as you move away. So two guys called Michelson and Morley set up an experiment where they shone light at right angles, and they found that no, in fact, there was no ether, or at least no ether like they could explain,
Hmm.
because they found that light did not, in fact, change based on the direction the Earth was traveling in. So, so the ether was essentially thrown out as a result. But then, of course, we come back to the idea of dark energy, and there's also the idea of vacuum energy. Because of quantum mechanics, there's actually in even pure vacuum, there's actually a certain amount of energy, because the probability, like you basically, the way quantum mechanics works is by probabilities, and specifically the one that really causes all this to happen, and this actually comes back to Helska 4. So this is, we're just segueing like pros here. But there's the Heisenberg uncertainty principle in quantum mechanics, which states that you can't know both the position and the energy of something perfectly. You cannot know them
Mhm.
both at the same time. The more precisely you know the position of something, the less precisely you know its energy, and vice versa. Technically, it's position and it's like energy and position and momentum, but position and energy are fine. So essentially, in the vacuum, because there's always like a slight probability, like no one's observing the vacuum. So according to the Copenhagen principle, which is another whole, or the Copenhagen interpretation, which is a way of looking at quantum mechanics, which essentially says that when you observe something, when you measure something, essentially, it appears where it is. Like that's the kind of Schrodinger's cat thing, which I won't go into because that's a whole other can of worms or boxes of cats. But basically, you get this vacuum energy as a result of this uncertainty, and that's actually been measured. You can actually put two plates in perfect vacuum, and they will slowly start to get pushed together by the pressure of vacuum energy. It's really weird and creepy. So having some kind of like rudder which could like move you around in said vacuum energy is another thing entirely, because these energies are so tiny.
Right.
Yeah,
really microscopic.
it feels
But
more like Star Wars is just treating it as like a Jello's in space.
Yeah.
And that's why you have drag and stuff like in atmosphere kind of behavior
of
in
course,
space.
and that makes and it makes complete sense, because Star Wars is ultimately based on
World War
dam
II.
busters and World War II and Vietnam movies and that kind of thing.
Yeah.
So from that point of view, it makes complete sense. And arguably, you could say that in Star Wars, sure, the vacuum of Star Wars isn't really a vacuum, and there is speed limits because of drag, and there is essentially like atmospheric style maneuvers you can do. But then I guess I would ask, why isn't the X-wing a lot more aerodynamic, and why are its wings just rectangular instead of producing lift? But
as it's cool.
And how does exactly. And ultimately, that's where most of this comes down to, because it's cool. I think definitely that Bantam era stuff is kind of reaching, and that's the kind of case where I think it's not worth trying to explain something and just go with it, because
it is cool.
yeah, because the explanation is just going to be less interesting.
Well, you were talking about with like the prior theories and with the aether filling that role. Is there anything that's kind of within our current understanding of physics that is generally understood by scientists to be kind of a placeholder, and that this will definitely get replaced by something that has a totally different picture of reality, but it's useful for now, so we're sticking with it? Or is it just typically
I would say
complete coming?
Personally, I would say that dark energy and dark matter kind of fill those roles, but I don't know, like that's just from my perspective,
right,
where most of my interaction with those theories was when I was an undergrad. If I read the papers in more depth, I'm sure I would appreciate the theories more. But definitely, I should note, the only reason they're called dark is simply because they don't emit photons, and we can't observe them as far as we know right now. That's the only reason they're called dark. It's not because they're spooky and weird. It's just because we can't observe them, which is in and of itself kind of spooky and weird, but for different reasons.
Yeah, like, I doubt there's anyone like working in their field that's saying like this is all just pointless, but just the idea that they're working with a much more incomplete picture of kind of that subfield of whatever they're doing, with an understanding that they're kind of at the basement or at the ground floor of what their field is.
Yeah, I think for me one of the prime examples of this, weirdly enough, is gravitational waves.
Why is gravity such a weak force? Can you tell us right now? Give us the scoop.
Oh god, I mean that's a whole. No, I can't give you the scoop because no one knows. Like that's a whole other. Like people have conjectured that there are multiple universes that are connected to ours, and that's why gravity is so weak, because it can leak between universes. Just wild things like that.
You just making stuff up.
Yeah, that's how it feels sometimes.
I feel like my high school physics textbook mentioned that one explicitly at some point.
Probably because they were like, "This will sound cool to some kids."
Yeah, exactly.
Well, one of my favorite examples that my high school teacher gave when talking about like the probabilities of everything, he said, theoretically, there's a probability that all the air in this room could just jump into that corner. It's not going to happen, but that is technically not impossible.
Yes, it's not impossible, just extremely unlikely. You could suddenly teleport to Mars, but for every single atom and particle in your body to do that is so vanishingly unlikely that it will never happen within the possible lifetime of the universe. Because one of the sad things about the acceleration of the universe means that we're probably heading towards what's called the heat death of the universe, where eventually all galaxies are so far away from each other you can't see other galaxies. They are only like locally gravitationally bound. And the final result of the heat death of the universe is you end up with a bunch of black holes that eventually evaporate, and you just have a bunch of like sad photons bouncing around in the cold. Like that's what happens with the current understanding of what's happening to the universe. That's going a long way in the future, of course, but it's still kind of creepy.
Bit of a
Depressing.
bummer.
Yeah,
Don't
it's a bit of a
worry, the
bummer.
sun will. It'll be long after everything on Earth is dead.
I mean, it's definitely a shame because the opposite scenario, a closed universe, is actually kind of fun because then it crashes back on itself and could potentially just create another universe again. You know, just you end up with this oscillation where a universe collapses down and just has to explode again.
Isn't
And you
there
just have you'd have what's called a big crunch.
Isn't there a theory too where like the Big Bang is not like a beginning point, but kind of just like a loop point, and time will eventually start moving the other way?
I don't think I've heard of that one.
I think that's
That certainly
basically the
sounds
same as the Big Crunch.
fringe. It sounds similar to Big Crunch ideas, yeah. Essentially, you have an oscillation where universe is just destroyed and reborn and destroyed and reborn.
That one sounds kind of epic.
So since we are talking about like one of the goals here is to maybe let people know how they can get into the field, there is a question I do want to pull from chat here from Tarkin, who is asking, do you think a physics minor would be hard for someone who does a math major and loves it but doesn't know anything about physics? So maybe just a bit about how to actually get into where you were.
I would say if you're a math major and you want to do physics, you're in a good position already because a lot of the difficulty that a lot of people have with physics is the mathematics. Now, that's not to say that physics is necessarily a conceptually easy thing to understand. It does take work. It does take sitting down and essentially running thought experiments, or if you prefer and you're more hands-on, really taking notice of what's happening in your labs when you do physics labs. The general path, the general path to doing my kind of career is it can actually be pretty varied. I personally did the kind of classic path where I did in the UK I did mathematics and physics as A levels, as well as a couple of others, and then in university I did physics for 4 years and got a master's, and then I went and did my PhD in physics. But I know, like, there are many institutions where professors will take you in even if you don't have a physics major, and you can become a graduate student in astronomy. So, for example, there's some colleagues who I've worked with who mostly worked in ecological sciences or in environmental science. So they have a bit of a science background, but they don't necessarily have direct backgrounds in physics or astronomy. You know, they'll have done some early classes in undergrad, and they'll have done stuff in high school, but they won't have a huge grounding. That ultimately just means that your grad school career will be somewhat more difficult because you will have to pay a lot more attention in classes. But the general path, definitely, if you're a mathematics major, I think physics is a great way to apply your mathematics to the world. It's a very exciting way, especially to me, to really say, well, look, I can describe what's happening in front of me by using 5 equations or less. You know, simple stuff like Newtonian physics, force equals mass times acceleration is such an elegant way to describe a very intuitive topic of where you punch something and it moves. Like that, it's such an intuitive thing, but to be able to describe that with mathematics is one of the like joys, I think, of physics in particular. Definitely moving from, like, I will say, like, if you want to go into research physics or research astronomy, you do have to go to grad school. And the path from there, the typical career path, which is, I will say, very difficult. It's not an easy path. Once you get to graduate school, you may find that it's not for you, and that's completely fine as well. The skills you will have will be very useful in many other fields. But once you've gone through graduate school, the current path is you will do one or more postdoctoral research positions, which is what I'm currently doing. I expect to be doing what I'm doing for another 2 to 4 years, depending on how well funding goes. And then after that, you will apply to be a professor usually. Or if you're exceptionally good at writing proposals, there are other paths, the so-called soft money, where essentially you pay your own wages by asking for money from funding sources like the National Science Foundation in the United States, or I'm not sure what it's called in the UK now, but there's a research council in the UK, and essentially you can just live off writing really good proposals and doing science. And there are companies that will house offices where you can go and work and do that kind of thing if you want a pure research experience. So there are definitely a few different paths available. And I think the biggest thing is really just always keep your options open and always try and stay aware of what's happening in research in particular. If you want to do research, especially now as an undergraduate, it's become even more important to try and do research as an undergrad. So talk to your professors, ask them what they have available. And that's always a good way to get into doing science and really finding out if it's for you.
Mm-hmm.
You mentioned like the high school stuff. It seems like a lot of what you learn when you're learning science ends up being a lie anyway. Like I remember taking like
Yes, that's
first level chemistry courses, and they're like, "Yeah, the electrons aren't actually here, but kind of imagine."
yeah. So I think what you have to remember is that you essentially the way that science is taught is as you get further and further into it, it makes a little more sense as to why science is taught to people in such a way, because kind of conveniently, the way that science in general has evolved through history is that simpler concepts have become more complex.
Mm-hmm.
So as you go through science in your career, in your especially in your academic career, you will essentially go through what scientists did in history, where you start out with the most basic stuff, like you sit in a bathtub and water is displaced, and then you get to the stuff where an apple falls from a tree, and then you say, yes, all these electrons are like little bullets going around a ball in the middle, until the end where you essentially say, well, it's all just a fuzzy mess and we don't know where anything is and nothing makes sense anyway.
Telling that to sixth graders probably doesn't go very well, yeah.
Right, exactly. And at a certain point, you don't like, there's a certain amount of detail you do not need to do certain jobs. Like you don't need to necessarily need to know quantum mechanics to work in programming, right? It's nice to know how a computer works, but you don't need to understand exactly why a semiconductor works like it does.
You barely even need to understand why a semicolon works how it does to work in programming.
So yeah, it's a windy road, and it can be very tough, but you really have to make that's why I suggest definitely trying out research as soon as you can, as soon as your university allows you to, because that's a really good way to get a feeling for what you'll like, because there's a lot of people who are way better at research than they are at coursework, and also where the reverse is the case, where they really enjoy doing coursework and they do really well learning, but when it comes to being to having to push that to do research and try and just deal with the vagaries of, well, my experiment is rubbish now, that can be difficult. So you really have to find where you stand on that kind of thing to really know whether you want to go into research. But that's kind of later down the line as an undergraduate.
Mm-hmm.
So depending on how early you are, you don't necessarily have to worry about that just yet.
I think that's a very satisfying answer to that question, hopefully. So we've talked about very big with relativity, but is there any evidence of quantum mechanics existing in Star Wars, do you think?
There's kind of evidence that quantum mechanics doesn't exist in Star Wars.
Okay.
Helska 4. There was a question about Helska 4 and the Yamosk, and all the weirdness that happens there. So for those of you who don't know, on Helska 4, was it Anakin Solo who decided to freeze the planet?
I think it was Anakin, yeah.
Basically, they use sun shields and reflect the energy from the Yamosk back onto the planet to evaporate the water on the planet, and through evaporative cooling, freeze the planet to absolute zero. And they even created a whole special name for the for the state the state the planet was in, like the atomic state, which was I thought was hilarious. But the problem is that you can't actually reach absolute zero with quantum mechanics. This comes back to that vacuum point energy idea. If a particle is truly at absolute zero, it has no kinetic energy, so it's not moving, and it has like no thermal energy. It has no rest energy.
So it violates the Heisenberg.
Exactly. You would be able to, if a particle was at absolute zero, you would know exactly where it was and how fast it was moving, which is impossible. So you cannot get to absolute zero because there will always be a small amount of what's called 0-point energy, which I think that in Half-Life they use that to describe how the gravity gun works.
Yeah.
0-point energy, which means that you cannot get to absolute zero. So there's the first part of Helska 4 that doesn't really work. The second part is that isn't quantum mechanics related to just a pure energy equation. If Helska 4 was the size of Earth and made of water, it would take about 10 days of our sun's total energy output to evaporate it. We're talking like just somehow reflecting Death Star levels of energy back onto this planet to evaporate it, and then somehow freeze it. But if you're putting that much energy into something, evaporative cooling will not work. It only works when you're not adding energy in. The reason evaporative cooling works is energy is being taken away through the process of evaporation via endothermic reaction. So essentially, heat has to be put in for it to, like, heat is taken out of the system as it goes.
Right. And if you're putting that much energy in, you might as well just blow the planet up, right?
Exactly. So that's why Helska 4 does not quite work. As far as other quantum mechanics examples in Star Wars, I don't know if there really are any. I think in general, Star Wars tends to stick to big picture stuff. There aren't. It's not like, say, Mass Effect, where you have the entanglement,
the
communications.
FTL,
yeah, which is a reasonable, actually, one of the more reasonable ways of having instant communication is by using this process called quantum entanglement, where you essentially that one's a whole other kettle of fish that I don't fully understand. It's very weird and makes no sense. I recommend finding a book about it if you're interested. But that's one of the slightly more reasonable, faster than light things in a sci-fi universe.
Do you think Luke was using quantum entanglement to appear on Crate in Episode 8?
I mean, if the Force is quantum entanglement, sure.
That's the one that I remember seeing when that movie came out. It's just like he's just using the Force. It's not science. You're ruining it.
It's magic, guys. It's magic. It's okay. It's okay. Like, that's the one thing I do want people to take away from this. It's okay to just say it's magic sometimes. And that doesn't detract from how fun Star Wars is. But if you do find a lot of fun in picking apart these things, then maybe you should be an astronomer or physicist or some other kind of scientist, because that's the kind of attention to detail and curiosity that really helps drive you through a career like this. You need to have that drive, otherwise it can be very difficult. So yeah. Do we want to move on to some more of the questions?
Yeah, sure.
Yeah, like, we've talked a fair bit about the shielding, so maybe we should talk a little bit more about the actual weapons and energy yields was something that was brought up, I think, in a few emails. So just
this
how
is the
much energy
Star Wars nerd question.
Yeah. The energy levels given for Star. I think you called these the Curtis Saxton questions for Star Wars technical commentaries.
Oh, God.
But so like stated values for how much energy is actually put out by some of these things and how that would interact.
So yeah, I think I called it the Curtis Saxton questions because if you go on his technical commentaries, you search for Curtis Saxton technical commentaries, you'll find a wonderful website with lots of it's a lovely, like, it's like going back to the 90s in web design. It's brilliant. And you'll find lots of very nice discussion about the technicalities of Star Wars from the perspective of an astrophysicist. And I strongly recommend you read that because it is fun reading. But one of the reasons that Turbolaser yield is so high in most, like, quoted books is partly because Curtis Saxton, like, helped write some of the
ridiculous
incredible
cross-section
sections. Yeah. And partly because he derived those values specifically from the cases where you have a known object being destroyed by a turbolaser. And that's the case where they're going through the asteroid field in The Empire Strikes Back. And the Star Destroyers are blasting away asteroids. And by knowing the size of a Star Destroyer and the
Composition.
and the well, it's literally he does crazy things like you look at the frame, you look at the size of the Star Destroyer, the size of the Millennium Falcon, and by using that, you can measure how far away the asteroid is, measure how big the asteroid is, and give it like a typical asteroid composition of, say, iron and silicon.
Mhm.
And then you determine how much energy it would take to vaporize an asteroid of that size made of iron and silicon. It turns out that energy is ridiculously large. We're talking huge amounts of nuclear bombs here,
Mhm.
like
Gigaton
megatons of
range,
TNT.
isn't it?
Yeah, gigatons,
Yeah.
even more. Yeah, ridiculous amounts.
Which is, it's kind of funny that he's using this kind of quasi-scientific method to determine turbolaser yield when, as you described earlier, he's in an asteroid field that in our universe probably would never exist.
No, I can explain why this makes perfect sense, because the reason it wouldn't exist, they'd all just kind of coalesce if they were that close together, if they were that massive. However, these asteroids are made out of styrofoam, so they wouldn't coalesce as fast. They wouldn't make such a large body. So you can have these more dense fields of styrofoam asteroids that are broken apart by much less powerful turbolasers. You're all welcome.
I mean, I think Corey has it. I mean, he's definitely right that if you had that much matter that close in terms of asteroids, you would start to get large amounts of clumping under gravity. And that's how we think planets form in general. You have essentially a relatively low density disk around a star. You have a density perturbation caused by something. Honestly, not really clear. Planet formation is a very complicated thing. And eventually that density just like causes a runaway effect where it will just coalesce into eventually a sphere, because that's the most gravitationally stable object. But going back to turbolaser power, ultimately I think if we assume that Curtis Saxton's numbers are correct, the easiest explanation is simply that turbolasers can be whatever yield you want them to be. And it's given the technology in Star Wars, that's not out of the question at all. And the questioner, the guy who asked this question, specifically mentioned things like when the Tantive 4 receives direct hits from the turbolaser, why isn't it evaporated? Well, they're trying to capture the Tantive 4, not destroy it. And when Kanan is driving through planetary bombardment in Rebels,
Adelon.
He's an atmosphere. So it seems likely that, and in fact, it's guaranteed that plasma going through atmosphere will lose energy, because atmosphere will get in the way. It will have to ionize the atmosphere as it goes down, losing energy. And by the time it hits the ground, it could conceivably have lost a decent amount of energy. Now, realistically, if you were bombarding a planet in that way, you would probably want to be running your turbolasers at the ridiculous max energy, and it probably wouldn't matter. But there's always the power of plot. And in this case, I would expect these turbolasers, if you wanted to estimate the energy, would be more on the range of what you would expect from a typical Earth-based artillery piece or Tomahawk missile. So about a kiloton of TNT effectively being blown up around. That's the kind of, it's the kind of thing you see in modern warfare movies or whatever.
Yeah.
That
Kanan's
kind of
right next to
explosion
them.
yield. Yeah, exactly.
He gets thrown by one and he's fine.
Well, he is a Jedi, so
yeah.
the Force is his ally.
Curtis Saxton also gives the like turbolasers a light minute range too, which I'd be really interested to see the explanation for that, given the fact that they move slowly enough that you can track them across the screen as they move.
Yeah.
Do you subscribe to the lasers are light plasma or light with a plasma tracer then?
I would definitely say that lasers in Star Wars are not stimulated emission. They are almost certainly plasma. There's no, because just the way they work, the explosions, what we know, unless even the thing is, even when you launch a single photon from a laser, which is possible, that people have made lasers where you can fire a single photon, which is a whole wave particle duality thing, which is another quantum mechanical thing. You can fire a single photon and it doesn't look like a single little blip of light going through, partly because light is incredibly fast, but also because that's just not how it works. I think plasma is definitely, especially because there's gas involved. In the other explanations for turbolasers and lasers, they mentioned Tabana gas. If you have a gas, technically that gases are used for lasers, because what you will do is you stimulate the atoms in the gas to all become ionized to the same potential, then they all drop that potential, and that kicks out photons of all exactly the same energy, and that's how you can have a focused beam of laser light. But plasma just makes so much more sense for the shape of them. Like, really, though, for them to have any range at all, what they would actually have to be is some kind of solid bullet inside that has a magnetic field to contain the plasma. Because otherwise, as soon as you fire plasma out of something, it would just dissipate, because all of the particles in there are the electrons are going to just join with the atoms and join with nuclei and form neutral atoms. They'll emit light. Essentially, you would just see a puff of light, and then it would just be gone, like if there wasn't some kind of containment field.
The destruction of Alderaan would look pretty weird, I guess, in that.
Well, the Death Star, that one is a classic laser beam, and that's a laser beam in the classic sense. And if we want a quick segue back to asteroid fields and planet destruction, because Corey, I know you were interested in this idea. In the case of in the case of Alderaan, that really comes down to how much force was involved in the explosion. According to Curtis Saxton, the acceleration of the debris from Alderaan was so fast that there wouldn't be anything left. It was all going at thousands of kilometers per second. And it was greatly exceeding the escape velocity of Alderaan. So these pieces, that's like if you sat on a rocket and just got flattened to the floor and blasted off, and just, well, you'd be dead to start with. But you were just shot off so fast, you end up in the moon in a couple of days. But if you give the Death Star a slightly more reasonable energy yield and a much lower escape velocity, a much lower velocity for all the parts, you could conceivably have a debris field from Alderaan that would be stable up to about the point the Millennium Falcon gets there. And there would be an asteroid field. Now, would it be stable for decades? Difficult to say. I don't know the actual timescales for planetary formation that would kind of cause these things to collapse in and on itself, but I'd say it's unlikely that it would be stable for the kind of time that it's stable for in Legends. Because the graveyard is still a thing all the way out to the Vong War, right?
Yeah,
I think they meet there during the Vong War at one point.
Yeah. There's still like the freighters flying around in it, waiting for Tycho Selchu.
Yeah.
Yep. Now, Malachor, which Corey also brought up in his questions to me, is an interesting one, because the idea of that is you have a large increase in gravity using this mass shadow generator. And what happens to Malachor is actually not completely unreasonable, because if you greatly increase the mass at the center of a planet, you would just start compressing it. This is much like what happens when you have a white dwarf, where the mass is not being held up by any kind of internal pressure, and as you start crushing it down, everything just has to get closer and closer together. So with Malachor, what would have happened is the whole planet would start to essentially shrink and be crushed down. And because the crust, because it was presumably a mostly terrestrial style planet before, it probably had a somewhat active mantle and a crust, which was broken into some kinds of tectonic plates. Those plates would buckle and crack, and you'd have mountain ranges be forming, and you'd have huge rift valleys, and there'd be lava and volcanoes and eruptions everywhere, because all of the lava in the mantle would start to be pushed out through the crust, and you would end up with a very broken looking planet. And then after that kind of that extra gravity is turned off, I'm not going to speculate on how it's a black hole again, I guess, but after that's turned off, you would get a relaxation. And I'm not sure how long it was between Malachor happening and it being visited in KOTOR.
Mm-hmm. It's like 3 years?
Yeah,
3 years.
only a few
Okay.
years.
In 3 years, it would probably still be pretty in the kind of crushed volcanic state of things, because in 3 years, you don't really expect the whole planet to like relax back, because you would end up with there would be pressure inside. You would essentially just have the surface start to kind of turn to molten lava, probably.
There's a joke in here about how it would take longer, but they didn't have enough development time. I'm too lazy to make it. So are they. Hey, it worked out.
Yeah, I think Malachor is actually in a reasonable state considering what happened to it. Bits being blown off it like they are in the game, I mean, that would probably be the kind of thing that planetary bombardment would have to do. I wouldn't expect simply crushing it would do that. You would most likely, just have a liquid surface after enough pressure is put on it. But other than that, it's not the most unreasonable thing in Star Wars, that's for sure.
So would that be like the kind of liquefied Earth you see with some earthquakes, or would you get any mountain ranges out of it?
I mean, you would definitely get mountain ranges, said rift valleys. I don't think it wouldn't be. So the thing you're thinking of is liquefaction. That mostly occurs due to vibrations.
Hmm.
Um, the liquefaction I'm talking about would be from heat and pressure.
Okay.
So you would start to break apart the rock and just crush it down like heat. It would get heated up by the pressure because of essentially basic laws of physics and gas laws. Even though it's a solid, you can kind of approximately apply gas laws to it. It would get very hot and become liquid, and you would start to get like parts of it would be liquid, parts of it not, depending on how long the mass generator was
Hmm.
turned on for, etc., etc. It would be a very traumatic experience for the planet and everyone on it.
Not for long though.
Probably not for very long, no. It would, well, the time scale of these things is another interesting thing to think about and calculate. Um, like the amount of time it would take to accelerate a planet's crust enough that it would start to liquefy and create mountain ranges and crack and put enough stress forces on it to cause it to break apart. That's an interesting thing to think about because, of course, gravity isn't instantaneous unless it is, I guess. If it's instantaneous, then yeah, it doesn't have to be very long. But in reality, gravity takes a little bit of time to turn on, as it were. It takes like, space time isn't immediately affected. It takes it moves at the speed of light. Gravity does. So, uh, yeah, it's it's a complicated question as to how long they'd have to turn it on for it to have the effects that we see. But you could probably calculate it with some assumptions.
Well, it does seem like it takes at least some time, but at least less time than it would take for them to come back and destroy the mass shadow generator. So I think that's what
Yeah.
your upper limit would have to be. Otherwise, it just raises other questions about how their society's organized. That's where we get our political scientists in. But that's my episode.
Oh,
But
I did mention there was a political science question. I believe, do you think modern technology that it would be entirely possible to successfully clone a human, create millions of copies, while at the same time creating a fake war to overthrow democracy and replace it with an empire?
that
I
would
believe
move
that's one.
actually we call that the Twitter constant in political science. You just have to put out enough fake memes and people will just jump on board that.
So that's how Palpatine rose to power, through fake memes.
Oh yeah, he was well known as a shit poster.
Okay,
Uh,
so is there anything else we want to discuss? Do we want to get? I've got a little bit of time. If you guys have time, we can go to audience questions for maybe 15 minutes, if there are any.
yeah, if you want to take a look at chat and see if there's any that catch your
Just
eye, I'm gonna take a look again at the emails that we had in our chat, as well as check the. Actually, do you want to check the inbox maybe one last time?
yeah, I'll do it now.
So I think even if we didn't bring up each individual one, I think all the points that were kind of brought up in the emails we got were pretty well touched upon.
Mm-hmm.
Um,
We covered that drift question. There's nothing really new since we started recording.
I noticed the guy who asked Willof Tarkin, who asked about becoming uh, uh, becoming a physics minor, wants to be a teacher, and I'd say becoming a teacher is an excellent idea. I love teaching when I have the chance to do it, and that's part of why I'm here, because I enjoy communicating with people and talking to them about science, and it's really rewarding to teach people. So good for you wanting to become a teacher. Um, uh, Will have also asks about what do I think of atmosphere capable star destroyers. I think that's fine if you have good enough shielding. Um, I think really anything can go into an atmosphere if you have enough shielding, because it really just depends on how powerful your engines are compared to the gravity of the planet you're above to make sure that you remain in orbit. Because the problem with atmosphere is that it induces drag. If you induce drag, you aren't going to be able to stay in orbit for very long. But
right.
given the power we see from Star Destroyer engines, I don't think there's not a huge good reason for why they couldn't go in atmosphere, aside from because it would be really bad for a lot of stories.
So Star Wars has repulsor lifts. It's some sort of like anti-gravity technology. Is
Yeah.
there any theoretical basis for that?
Again, I think that would probably come back to the usual exotic matter / negative energy kind of scenario,
Right.
where essentially to have that kind of repulsive force, you need something that is pushing in some way, and negative energy is good for that because it has negative mass and a lot of other weird properties that mean you can do that. I mean, essentially, what I would consider Star Wars repulsor to be is the opposite of, again, whatever internal ship gravity they use. You invert that technology, and instead of attracting, it repulses, and ta-da, repulsor lifts.
So there
I mean,
is
sure.
there is another question in chat here from Tritone who wants to know your thoughts on single biome planets, and I would like to add an extra wrinkle to that. Is that would a binary system, if you were to somehow have if you were to have a habitable planet in that, would the fact that there is a binary like two stars or maybe even more suns, would that be something that you'd expect to impact life on that planet in a significant way?
Yeah, so in terms of single biome planets, they are, I would say they're somewhat possible in the sense that, Mars is almost
Yeah.
a single biome. Uh,
Single biomes that aren't boring.
I mean, Tatooine's a single biome that's kind of boring, but a planet that's entirely forested isn't completely unreasonable. You just have to have it close enough to its star where you wouldn't be able to have uh, water ice at the pole in the cold regions. And then, even with some amount of water ice, it would be still reasonably valid to have a completely forested planet because plants are incredibly versatile. And aside from the equator potentially being too dry or too hot, I couldn't think of a good reason why you couldn't have an entirely forested planet. Now, would it be the same kind of trees and the same kind of plants all the way across? That's very unlikely because certain adaptations are good for certain climates. Like
Mhm.
Endor wouldn't necessarily do very well as a planet covered with sequoias. But on the other hand, it's a moon, and moons would have very, very different kind of timescales of seasons and seasonal change because it depends how fast they're orbiting their planet and how fast that planet is orbiting its star.
Mm-hmm.
That would really affect the seasons on Endor in particular. You could have an entire like decades of dark season if the moon was orbiting its planet slowly enough. Now, Endor's really seems to be really close to its gas giant. I should say Endor is the gas giant, of course, it's the forest moon. But the forest moon seems to be very close to its gas giant, therefore it's probably orbiting quite quickly. So they wouldn't have extremely long dark periods.
Mm-hmm.
But there's a whole load of questions about the rotation rates and stuff that would affect that. Um, Binary planets have a kind of similar problem to habitable moons in that their seasons are extremely strongly affected by the fact that you have multiple orbital elements going on.
Mhm.
So there'll be because just because of physics and the way rotation works in physics, if you have a binary planet, a planet orbiting binary stars, they would almost certainly be in the plane of the binary star's orbit. So there would be the chance for the binary stars to eclipse each other as the binary stars orbited each other. This is assuming that you have a planet that is what's called circumbinary. So it is orbiting both stars at the same time.
Mhm.
In that case, you essentially get quadruple seasons because there'll be times where both the stars are putting light onto the planet, times where only one star is, and times where the other star is. And if the stars aren't of equal brightness, you'll have like a ridiculously hot summer when both stars are shining on the planet. You'll have a really cold winter when only the dim star is able to shine on the planet, and a warmer winter when only the hot star is able to shine on the planet. So you'd have this really weird seasonal system. The other way you can have a binary star system is actually by having the planet orbit just one of the stars in the binary. And then the seasons get even wilder. You can have imagine where the planet is between the two stars. There is no nighttime on that planet for that day. Like the planet will be rotating probably, and there will be no nighttime because you're being shone at from both directions.
Mhm.
Mm-hmm.
So There would be some very strange. If life evolved on planets like that, they'd have to have some very strange cycles. You certainly wouldn't be able to have typical sleep cycles, depending
Well,
on the length of the year and so on.
probably just born with sunglasses on, if I'm being honest. So binary stars are cool, but is there a like a limit to the amount of stars that can rotate like securely with a planet involved? Like, could you have like
Not
a
I mean,
7 stars or?
I believe there was a system discovered recently that has. Now, I don't think it has any planets discovered with it, but there was a sextuple star system,
Hmm.
which is like, I believe it's two sets of binaries orbiting another binary, um, which is pretty wild to think about. The problem is that the more large, massive objects you add to the equation that are orbiting each other, the less stable it becomes.
Mm-hmm.
There's a classic thing called the three body problem. When you have one object on its own, it's fine. When you have one object orbiting another object, it's fine. When you have three objects, you start to get chaos involved
Mm-hmm.
and perturbations that become very unstable very quickly.
See
And
one
it's
just get
been
like ejected or.
Yeah, exactly. So it's been very, very difficult for scientists to simulate how planets could form under those conditions. And that's actually one of the biggest problems, I would say, in planetary science at the moment, really understanding how planetary systems like our solar system can be stable over a long enough period of time for, say, life to evolve.
Mm-hmm.
With binary systems, do you typically see, would you be more likely to see stars that are of equal brightness or of significantly different sizes and brightness? What would be kind of the more common, the mean system?
Well, the mean, I'm just going to drop a paper in chat, which is actually pretty interesting. Tells you about season, like the amount of light that you would get for a planet orbiting a binary system. But for like really the average star is a red dwarf on its own, which is dim. It's lives for billions and billions of it lives for hundreds of billions of years potentially. They're dim, they're boring, they're basically a bit heavier than Jupiter, just heavy enough to burn in nuclear fusion. In terms of binaries, I believe the majority of binaries are relatively similar in mass and type, but you only have to have a small disparity for there to be a big effect later on. So the stars so as part of the supernova work I do, I study binary stars, and in particular, very massive binary stars. You wouldn't want to planet around those because they put out huge amounts of UV radiation, and you'd have to have a ridiculously thick atmosphere to be safe from the UV radiation from massive stars. They also don't live very long. They will explode a supernova on the order of hundreds of millions of years rather than billions of years. So what happens if those two stars are slightly different ages? One of them will evolve further and become either a red supergiant or a what's called a Wolf-Rayet star. And they essentially they swell to gigantic sizes, and they will actually start exchanging mass with their companion. Their stellar winds will interact, and that can cause X-rays to be created. You don't want to live in one of those systems. They're really cool to study, but they are not somewhere you would want to live. That's for sure. Just based on what I know of stellar populations, though, the average binary system would probably just be two stars, somewhat like our sun.
Mm-hmm.
So you would get some interesting seasonal effects, and again, you would still have evolutionary difficulties where later on, if one star becomes a red giant first, which is what our star will do, become a red giant, not a red supergiant, just a red giant, and it'll swell out to about the orbit of Mars. When that happens, again, obviously there will be some problems. You'll start to get mass transfer between the stars. Weird stuff will happen, but people on planets will be having a much worse time just because of the red giant at that point, and they won't really mind about what's happening to the other star in the system.
That sounds very pleasant. So you need SPF at least 30 for that.
I would say so, yeah.
Being consumed by a red giant. I think that's pretty much all the time we have. Is there anything else you wanted to add, Corey? We've taken a lot of Dr. Fullard's time.
No, so actually, we have mentioned a few papers that you wanted to drop in chat. So what I think we'll do is if you send me anything that you kind of want to add as additional notes or links. I'll put those in the audio version of the podcast. I'll put them in the links there, and I'll add them to the description of this video version later as well. So if people want to check any of that out, that'll be available on whatever description of whatever podcasting platform you're using, or in the YouTube channel video description as well. But is there any other topics you wanted to just get to at the end here before we go, Andrew?
No, I'm fine, thanks. I think this was thanks so much for the opportunity to talk to people about this stuff, guys. I hope this has piqued some people's interest in astronomy and got you some fun facts about how Star Wars does or doesn't work.
That was fantastic. Thank you so much. That was very interesting.
Very cool.
I'm sure a lot of people will find that both very interesting and very helpful if they want to get into the field. But is there any pluggables you want to plug of your own or professionally, or anything you want to draw attention to?
You can follow me on Twitter at Astro Fullard. I mostly just retweet other people, but sometimes I tweet about my own work and about other general science topics. Obviously, subscribe to Thrawn's Revenge on the workshop, because I write most of the AI for that. So if you lose, you lost to me. If you win, I had nothing to do with it. And I guess Phoenix Rising as well. I work on that mod, though not as much recently. I should get back to that. But yeah, I think that's everything.
All right. Well, thank you again for taking so much time to come and talk to us laymen's. Thank you also. I want to give a special thank you to Mr. EckhartsLadder for behaving himself this episode. I know
You're lucky.
I'm very happy with that, yeah.
Corey, you're just as badly behaved as me. Come on.
I'm an enabler.
We're
I'm
like
an enabler.
twin...
You're the problem.
No,
okay?
no. We're like the binary star systems that are ejecting our bullshit into each other for everyone to watch. I don't want to hear anything else.
All right. Well, we won't plug Cart this time, because that's what we're doing after this. But thank you again, Dr. Evil Bob the Bob. That's been the hardest part for me, is deciding what to call you in any given moment. But hope you've all enjoyed this. Maybe we'll have you back on again sometime to get to maybe some of the questions that we didn't have time for, if there's any more questions, if you're interested. And bye, everyone.